Hello, and welcome back to this video. From now, we pretty much enter the last territory of this course. We will study a little, just a little, estimation methods on parametric models. Here is a quick overview of this chapter. Actually, we will not focus on all of them. Instead, we will cover 1 and 2. The rest obviously are also important. For instance, Bayesian estimation is essential in statistics and has many, many applications in actuarial science. We will actually study Bayesian estimation a lot in the next course. So if you are registered in Math 5640, you expect to learn a lot on Bayesian credibility next semester. The fourth one, it's not that well known, at least, but the last one, copyright, it's so popular in actuarial science. But nevertheless, we only have time to cover the first two methods. They are on the elementary side, but still, the application of those two methods or three methods are rather standard in statistical literature and also the applications in actuarial science. So now, without any further ado, let's begin the first methods. There are actually two methods. They are very similar. So let's begin with the well-known one called the methods of moments. Here we have some basic setup. Let small f be the PDF or probability function of a loss variable x. Here theta would be some parameters to be estimated. Of course, that's because we are under the framework of parametric estimation. So our objective is to estimate those thetas. So in order to achieve this purpose, so basically here we have k parameters to be estimated. Sometimes it will be less than k if some of them are given. We are trying to apply the moment matching method. In order to use this method, we need to compute the moments, right? So here we introduce a notation, mu with subscript r, that r denotes the r's law moment, and then we put apply to denote this is the law moment from the true model. In other words, this is the definition of this. And the expectation is taken under the true probability, or F. But of course, well, since thetas are unknown, this generally will be a function of theta, right? For instance, if you consider a normal distribution, the first moment will be equal to mu. Mu is a parameter, right? The second moment will be related to sigma, both sigma and mu. So those are the two parameters in a standard normal distribution, right? Okay, so that's the theoretical side. Now we want to match the theoretical result to our empirical result. Okay, for empirical result, we're going to put a hat on top. So the rest is the same. So if you do a quick comparison, this is the theoretical value. And then we have an empirical. Okay, so we have a hat on top because it's an empirical estimate. So as you have already imagined, we apply the standard empirical distribution. So there are n observations. We assign equal probability to each of them, meaning each of them has a probability of 1 over n, okay? So this can be easily computed as long as you have all the available observations, right? So now we do the matching, right? Matching means you match the theoretical result with the empirical result. So here we have k parameters. So we are trying to set up k equations, okay? Starting from the lowest moment, that's the first moment, all the way to the kth moment. We prefer to start with lower moments. So if there are two parameters, we use the first and second instead of the second and the third, okay? That's our preference to start with lower moments. That's because for some heavy-tailed distributions, higher moments may not exist. So let's say a Pareto distribution may have the first moment, but may not have the second moment. So this gives us an advantage to always try the lower moments. Then we basically, what we have at 12.2 is a system of equations, right? So they are actually k equations. Given k equations, we are trying to solve for k unknowns. Well, not always we can find a solution, right? But here we assume we are able to find a solution from this system. Okay, this is our assumption. In most of our examples, this is indeed the case. But of course, it could be some counter examples under those you will not be able to find a solution. It's possible. So now let's take a look at the example. We have example 12.1. X here is the claim frequency. We study three choices. The first one is a Poisson. For Poisson, well, we already know, right? For Poisson, the theoretical mean is the parameter. So that's what we have done here. The first one, the expectation is equal to lambda. And since we match to the moments, it will be the sample mean. So we use X bar to denote sample mean. Well, we just need to match, right? That means lambda here. For estimator, we put a hat. So this lambda is the true parameter, okay? Whose value we don't know. We are trying to estimate this true parameter. Of course, it's a constant, right? So we are going to use the sample mean to approximate or to estimate this parameter. So that is the meaning of this notation. So when you have a different sample, you're going to get a different X bar, right? So in applications, what you do is you need to fix a sample size, okay? And then you need to consider how many runs you want, right? In the first run, you get X bar. I put superscript 1 to denote this is the first run, right? And then you can do the second run. I will get another X bar. You do it n times, and then you can do average of average, right? This might provide a slightly more accurate estimate than just relying on one sample. But again, we only study the simplified scenarios. So in our case, we don't do this. Well, this is Monte Carlo simulation. We don't do that. We study the basics. Right? So here we use the sample mean to approximate the true mean. So that's what I mean. The next one is geometric. This is the mean of geometric is 1 minus theta divided by theta. Again, different textbook might have different definitions of geometric, right? So this is our definition. I match the theoretical result to the empirical result. Then this is the equation of one parameter, theta, right? I can easily solve this to arrive at this estimator. So this is an estimator. So whenever I have a sample, I can compute the sample mean. Once I know the sample mean, I know my estimator for this theta. For the same reason, when we have a binomial, we know the mean is m times theta. So here, theta is the unknown parameter. M is something we know. So m is something we know, so we just divide by m, right? What if both m and theta are unknown? then we need to go to the next moment, right? Then we need the second equation to help us solve this, right? That is something actually we do in the next example. Example 1, 3 sub-questions. All of them have one parameter to be estimated. In this example, we actually have 2 parameters. Here we study claim civility. We have 3 distributions, right? This is not geometric. This is a gamma distribution. The first one is a gamma. The second one is a Pareto distribution. The last one is a uniform. It's obvious that all 3 distributions are parametric, and all of them have 2 parameters to be estimated. That means in this example, we not only need the first law moment, we also need the second law moment. By the way, I should mention that here we always study law moment. That's because the empirical version is unbiased. So here's unbiased estimator. This is not the case when you study the central moment. Right? Obviously, if you study central moment, let's say the second one. This, if you take expectation, this is not equal to your variance, right? This is well known. You need to divide it by n minus 1. But if you divide it by n minus 1, you change the empirical distribution, right? Empirical distribution means that all the observations have the same probability, 1 over n. But if you divide it by 1 over n minus 1, then it's not exactly the empirical distribution, right? So that's why we actually prefer to use law moments. Of course, when your sample size n is large enough, the difference is rather tiny, and in that case, you may want to use central moments, right? And since the difference is negligible, then it doesn't make a huge difference. But here, to us, it's important to make that remark, since sometimes we only have 10 observations, right? Then 1 over 10 and 1 over 9 are quite different, right? But if 1 over 1 million and 1 over 900,099, but then it doesn't really differ that much. So here we do the same thing. We need to know the first moment and the second moment. Those are given by the known formulas, right? Okay, I have 2 unknowns. I have 2 equations. Technically, I should be able to solve them, right? And that's indeed the case. We replace alpha, beta. So here, right? So I can reduce into an equation just of beta. So I solve for beta first. Once I know beta, I can plug in this equation, the first one, to get alpha, right? Remember, whenever you get an estimator, put a hat on top, because the true one we don't know, right? The true alpha and the true beta are always unknown. So that's why when we get the estimator, put a hat on top to denote they are estimators, not the true values. For the second one is Pareto distribution. This is a heavy-tailed, and from here you easily see that we need some assumptions, right? Pareto distribution is defined for, or at least a standard Pareto distribution is defined for positive, right? For positive x, well, if x is positive, the expectation obviously must be positive as well, right? So here, your parameter gamma is always positive, meaning in order to have a meaningful first moment, your alpha should be greater than 1, right? And then if you look at the second moment, it must be positive as well, right? So alpha actually needs to be greater than 2 in order to have the second moment. In fact, if you want to have higher moments, you need alpha to be greater. So there are restrictions on the parameter alpha, right? So here, let's assume for a moment that we have no issue dealing with everything, okay? Then we can solve this problem. Well, there are different ways you can try, right? So for instance, you can square the first equation, right? And the first equation, well, divided by the second equation, you are able to cancel the parameter gamma, right? Then it becomes an equation of only one parameter of alpha. So we are able to solve alpha first. Once you are able to solve alpha, you can plug in anyone to get gamma, right? Of course, as I already mentioned, there are some conditions, right? This condition means you don't have the variance term, right? No, you don't have it. You get a negative variance, right? Obviously, it doesn't make sense. So we need this to be greater than 0, okay? The last one is uniform distribution. It's obvious this is the mean, and this is the variance, right? See that? We don't directly match variance. Instead, we match the second law moment. That's why we use variance plus the square of our mean to get the second law moment. Then we can do the matching and try to solve this system of two equations, right? A and B are unknowns. It takes a little effort, right? You are trying to solve a quadratic equation, right? So you should be able to get this answer, and you need to note that B is greater than A. So that's why here is plus, here is minus, right? Then obviously A hat will be less than B hat. We have a quick note as well regarding this special distribution, right? We might have this. Uniform, the meaning of uniform is X is between A and B, right? So for all your observations, they are supposed to be within this range, right? Greater than A, less than B. If they are out of this range, so let's say the minimum is less than A hat or the maximum is bigger than B hat, then it's incompatible, right? So what we just estimated does not match the theoretical property of this special uniform distribution, right? Well, of course, you can take the maximum down here, or not with the minimum, and well, you can take the smaller. If this is bigger than the maximum, you can cap at maximum, right? But that changed the story. Once you put this, it no longer matches the first and second moments, right? So those are the possible issues. So here is one, and we also mentioned in the Pareto distribution, you might also have some issues. Let's take a look at example to see how we can do estimation for censored data. So here we have ground up losses, and we have 15 observations. The original distribution is a uniform between 0 and B. So now what we want is we are trying to match the so it's like we apply a policy limit, right? And we know the policy limit is 15, right? Well, this does not change too much, although this let's take a look how we can do this, because we already have the data, so we can easily calculate the empirical version, right? Empirical version is very easy to do, which is already obtained down here. what we still need to work on is the theoretical value, right, of this, given X follows a uniform distribution. Here is the computation, right? We apply the method from survival distribution, right? So this is a well-known result. Well, of course, we can also do it by definition, right? So when X is between 0 and U, the minimum is X, right? And I know the probability density is 1 over B. So whenever X is greater than U, is capped at U, then I need to know the probability of it. Obviously, it will be 1 minus U over B. Okay. By the way, here I should already mention that B should be greater than 15, right? So that's something you should keep in mind. Okay. Otherwise, this will give you a negative value. So if B is greater than 15, here my U is 15, then 1 minus U divided by B will be positive. Okay. Well, this obviously will give you the same result as this. So now we match, right? We match this to 9.3333, so it's 9 plus 1 over 3. So you do the matching. U is already given, which is 15. So you easily get this result. Okay. So that's how you do the censored data. Of course, you can also do the same thing when there is a deductible. I believe there is an example. Is an example down here, right? Okay. So I put this example. This also comes from the textbook. So here we have 10 claims with deductible 5. So there is a deductible we need to consider. What we have down here are 10 observations of ground up loss. So what we can assume is, according to the information, the ground up loss follows a Pareto distribution. So there are 2 parameters, alpha and gamma. But now we have a deductible. So we do not directly fit the data with the ground up distribution. That's because we actually need to apply deductible, right? So of course, this is not complicated. When you apply deductible, it's simply you minus everything, right? So this is what you do when you apply with deductible. So here all of them are positive. So what you get is 7, 8, 9, etc. Right? So everything minus 5 up until 92. So we have n equals 10 of them. The next thing is, what is the distribution of this? We need to know the theoretical distribution of this modified distribution, right? So let's put x tilde to denote this. Well, according to what we studied previously, we know this is also a Pareto distribution. The first parameter remains the same. The second one has to be changed. So this is the theoretical result. Once we know this, things are reduced to the previous result we studied. For instance, I believe it's here, right? So here we also do the Pareto, but for the second one is gamma plus D, and D is 5. So we do the same thing, so you should be able to get the result. This will be different. So from here, you will get alpha and beta, gamma. So this it should be different from your estimation if you use the raw data to fit the original distribution. Okay. That's everything about moment matching. Moments obviously are very important characteristics of a distribution, but there are many other characteristics we also like. One of them, another one is percentile or quantile. This is sometimes also we call quantile matching or percentile matching. Those are the same meaning. We actually studied a lot of quantiles in the risk measures chapter. Remember, quantiles is pretty much the value at risk, right? So we spend a lot of time calculating quantiles there. The ideas are the same, essentially the same as the moment matching. Now we are trying to match the quantiles. So we calculate the theoretical quantile, and then we calculate the empirical quantile. One thing I still want to mention is when you estimate theoretical empirical quantile, divide by n+1. Okay, this is different from the law moment estimation. Well, everything is 1/n. So here, when you do the quantile estimation, you actually need to divide by n+1. That's what we dealt with in the last chapter, right, under the non-parametric estimation. Other than that, everything is just as expected, right? But here, we don't have exactly criterion as what delta should be chosen, right? Remember, under the moment matching, we start with the first moment, we then go to the second moment if there are 2 parameters, right? If there are 3 parameters, we will do first, second, and the third. But here, quantile, delta can be anything between 0 and 1, right? Should we pick 10%, 20%, 50%, or 90%? Right? There are no universal rule that everybody agrees. So, sometimes, oftentimes, different choice of delta will lead to different results. Somehow, rule of thumb is do not use extreme quantiles. For instance, don't use 5% or 99% because those are relatively volatile. If you pick something in the middle, they are more robust. Like let's say pick the median, 50% or 70% or 40%. You know, those are safer, right? Relatively speaking, they are safer with respect to the changes of data. But that's not something we need to worry because I always tell you, you know, what percentile you should choose, or we should develop a general formula. Let's use an example to demonstrate how we can utilize this idea to estimate parameters. Here we have a Weibull distribution. It has 2 parameters, alpha and lambda. There are 2 parameters, meaning we need to pick 2 quantile levels, right? So let's say delta 2 is bigger than delta 1. Right? So here we do the general analysis, so we don't care the exact values of them. As long as they are between 0 and 1, they are good. This is the CDF of Weibull. Obviously, X delta is the delta level quantile. Without hat, meaning it is the theoretical version. Okay, solving this is not complicated, right? We are able to arrive at this system of 2 equations. Both alpha and lambda are unknown parameters. So obviously, you know, you do a ratio, you are able to get rid of lambda, right? Then alpha becomes the only parameter in this new equation. It's easy to solve this, right? Once you solve alpha hat, you can plug back into any one of them, either 1 or 2. You will be able to get lambda hat as well, right? This is a nice example because first of all, we are able to eliminate one of the parameters to arrive at an equation of 1 unknown. And even luckily enough, we are able to solve this explicitly, right? In most quantile matching examples, you may not be able to get the explicit expressions like this. So let me give you an example. Suppose X follows a Pareto distribution. So apply the quantile matching. First, we need to recall a result of Pareto. That is the CDF. It's given by this form, alpha. Okay. So now we are trying to do the matching, right? So what we pick any 2 different levels, delta 1 and delta 2, and we establish this equation. That I equals 1 to 2. Okay, then we obviously we need to use theoretical work to estimate this quantile, but nevertheless we need to solve this first, right? We can move it to this side, and since we take a log, so alpha will come in front, right? And obviously we can do a ratio to get rid of alpha. Then I have this. This is an equation of one unknown, right, of gamma, but I wouldn't be able to actually solve this explicitly. Of course, you know, with any computer software, you can easily solve this kind of nonlinear equation, right? So for instance, in MATLAB or in R, you can solve this easily. So assume you use some software to solve for gamma hat. Once you know gamma hat, then you can plug in any one of the equation, right? Either equation 1 or equation 2 to get alpha hat. So that's often the case, right? Only for very few examples, you are able to solve the quantile matching in theoretical results and get nice explicit expression like this. For instance, exponential, well, you will be able to get explicit result. For normal distribution, you don't even have a nice expression for the CDF, right? But numerically speaking, quantile matching is very easy to achieve because nowadays, pretty much all the known distributions, the software has built in quantile results, right? So we can easily get the quantile for any distribution we want, and the matching means we are trying to solve a nonlinear system. Again, that can be easily done in any software. So from a numerical point of view, it's very easy to implement. Okay, that is the first part of section 12. So I will end here. In the next video, we will learn maximum likelihood estimation.